From Cambridge, talking about conformal field theory of regular algebras and the Fuchsian equation.
Well, it's a pleasure to be here. Long time ago, Konstantin and I, Peter Goddard, Richard Borchards and others had our conformal field theory seminar in that little room there. And in fact, in the entrance hall here, I think back in the original days is where I worked out how to do fusion for SU2 using primary fields, which is what I'm going to speak about today. So this has some quite happy memories. I'd like to thank the organizers, Vaughan in particular, for inviting me here. Okay. So here goes. I'm using this ancient technology which they've rescued from some room in the basement. It's like using video recorders instead of DVDs or something, VHS. Anyway. So what I'm going to talk about, so it's operator algebras and conformal field theory with a number after it, which is probably a Greek letter by now, or EFG. And the main idea will be to have a way of solving one of the central equations in the theory, which is called the conditioning Samologikov equation. And that will reduce to the symmetric Fuchsian systems, which are very simple things where you can forget about any group at all. So if you don't know anything about E8, G2, or anything like that, these just wipe all that away and say, forget group theory, we're going to solve the equation without using that. So the idea then is that it's a new approach to the KZ-ODE, conditioning Samologikov ODE, which applies to the exceptional groups EFG and most of the other ones for particular representations. So the main tool for fusion of positive energy representations of loop groups and subfactors, which are defined by the failure of Hague duality, is this KZ-ODE. That's kind of the central thing. And if you think about Vaughan's planar algebras, there are some little boxes there which contain all the goodies. This is such a box with a great goodie inside it. And as I'm going to present it, I hope it will be something that if you're stuck on a desert island, you could rediscover it if you had a pencil and either a postage stamp or an envelope on which to write. So it's a kind of thought experiment way of solving the KZ-ODE. So those subfactors which you've seen before, let me just remind you of what happens. There's a picture, a circle broken into two halves, an interval and its complement, and that is the sort of the breaking of the symmetry, which is this failure of Hague duality that Vaughan and I did back a long time ago in 1989 or 1990, somewhere in Paris. Anyway, hypergeometric, so the things that arise here will be hypergeometric ODEs, ordinary differential equations and modular forms, and link between them, which Terry Gannon and his collaborators Bante and others have pushed, and that's kind of very much underlying the philosophy here, although it's not really needed, but it is just important philosophically. Then there's a linear rigidity theorem for monodromy, which anybody could do after doing linear algebra 1, well certainly here in Cambridge and probably in Berkeley as well, or anywhere else. So it's just some very elementary linear algebra. And then there's a direct approach which we'll use, a kind of genericity result, like the result that says every invertible matrix is the product of a lower triangular times an upper triangular. So that's kind of the Gauss decomposition. That's almost true. It's true up to an open cell. And there'll be a similar result here, which will allow us to do this thought experiment computation of the monodromy of a differential equation. So this goes a little beyond what Hans Wenzel and his student Imre Tuba did, where they had a set of rigid representations for the braid group in dimension less or equal to 5. This sort of goes up in all dimensions, but with obviously specialized to that, and all these dimensions are sort of related to each other. Okay. So what is a symmetric Fuchsian system? Well, you have the objects there, so you can have some minimal things. So you have this CP1, the Riemann sphere, so the complex numbers with infinity adjoined. That's acted on by this group of complex Möbius transformations. And then you have this group, which you can sort of look up on Wikipedia, the anharmonic group, which stabilizes 0, 1, and infinity. And that, so you know that any Möbius transformation, you can take any 3 distinct points to any 3 other ones. So this is kind of a sort of canonical thing. And you can just see the 6 transformations which generate that. So that gives you a copy of the symmetric group on 3 objects. And you can see the generating matrices are just those 2. This one, you note, has determinant -1, which is, I mean, if you put determinant plus 1, then you be into SL2Z. So that's a kind of just something which you have to kind of be a little careful of. Well, this has 3 irreducible representations. Well, the trivial representation, which changes the involutions, it sends those everything to 1, and the sign representation, which takes the involutions to -1 and the things of order 3 to 1. And then a 2-dimensional representation, which you can write in that form. And it's integral, so that's kind of, it's Young's canonical form, if you want, anyway. So now what you take is you take an S3 module, for the symmetric group on 3 objects V, and you assume that if it's even, it breaks up as a sum of 2-dimensional representations like that, and then a trivial and a sign representation. And if it's odd, it breaks up as a sum of 2-dimensional representations and then just 1 copy of the trivial representation, or it could just be 1 copy of the sign representation. It doesn't really matter. And then you look at this differential equation, which I've written kind of in connection form. So you have these matrices A and B, and if you were to, this is actually on the sphere, so if you move it to take the coordinates of the sphere, you get C equals -A minus B for what you get at infinity. And then the condition for it to be symmetric is that you have this action on the vector space and an action on the base space, and you just say that it be invariant under those 2 joint simultaneous actions of S3. So that's it. Well, the key example, so I said, somehow this came from a group, and we're going to forget it, we're just going to keep that data, is the condition examiner logic of ODE. And so here you take G, a compact group, acting on a vector space W unitarily. German G is, Gothic G is, or mathfrak G, what did you call it, mathfrak G, for latex users. It's different for plain tech users like me. We can't communicate with the rest of the world. It's like this video projector, it's out of date. So Lie algebra of G, you take an orthonormal basis of that, regarded as sitting inside the Lie algebra of the orthogonal group, and then you just form these 2 elements with a constant which in the examples will depend on the level. It'll get right. And so you have these 2 operators acting on the 3-fold tensor product. Also, the symmetric group acts on the 3-fold tensor product by permuting the tensor factors. And then you take U, an irreducible representation of G, and then look at that multiplicity space for u in the threefold tensor product. And then this form here is an example of one of these symmetric Fuchsian systems. Just forget the group now. You've thrown it because you passed to the fixed points. You've lost the group, and everything we do will not. We won't try to remember the group at all. It's just one of these things. So I should say that there is a technique for doing these things so we don't forget the group, and we go into quantum groups. So we do the Reshetikhin-Kirillov construction, which, if we were to do it for E8 with this kind of some five-dimensional thing, would be uncomputable. Likewise, we can do the free field theory of Felder et al., which was sort of put into formal language by Farshenko and Shechtman, and that again involves all these extra variables in a huge number, as many of the roots of E8, and then you can't do anything. You can't manipulate them. I mean, you can't even say what they are often. So that's why we've kind of thrown the group out and just stick with this. Okay. Right, well, classical invariant theory. So we've seen all this before. I didn't just go to the other talk so that I could work out what I didn't have to say. But anyway, we have seen some of this before. So classical invariant theory and subfactors. So these subfactors are integer subfactors, and they're regarded as the sort of limit cases where you have the index will be the dimension of this vector space V squared. So what you take is you take nv tensor to the n, and these increase. Imagining having identity, infinite tensors with identity almost everywhere, and you fix under G. So V is a G module, a unitary representation of G. Now this contains S infinity, the infinite symmetric group, and that's because it just permutes the factors and commutes with the action of G. And Scherval duality says that when G is the unitary group of V, the commutant, or this fixed point algebra, is just S infinity. And the usual way we draw it, there's a picture. We've seen lots of pictures. This is a picture before you quantized, so things cross. And that's an example of a permutation. And you'll just generate everything by these kind of diagrams where infinitely far out you just have straight lines going down. Now, invariant theory, so what you read in the book of Hermann Weyl on classical groups, or in the book of Dieudonné, also on a slightly different view of the same subject, shows that when you take a different group than UV, you find that the invariant theory, there are only finitely many extra elements you need to give the invariant theory, which is also something we know from subfactors. It's kind of principal graph, and how far you need to go out before you get everything. And in the case of SOV, you get the Brouwer algebra with this sort of primordial Jones projection known to Brouwer and Weyl, and that's just a contraction. So it's just the projection onto the trivial representation in V tensor V. So the sigma EI tensor EI. Right. Well, given this duality, for the unitary group, you could index the irreducible representations by Young diagrams. That's what happens for the symmetric group, so that there's that kind of duality. And you have the usual multiplicity 1 rule for tensoring with a vector representation. To a Young diagram, you add it wherever you can, and if you can't, you don't add it. And so you have a kind of multiplicity 1 rule. And here, I hope I haven't made a mistake, are the known rules for tensoring representations of SU2, which, and of course we take so spin J, and I take Arthur Jaffe's convention or Vaughan's convention or anybody else. I think we all do it that way. Well, so there's Hermann Weyl's book on the classical groups, which does not mention the exceptional groups. And in fact, the approach to we're here at a CFT conference, the right way of doing exceptional groups is to do the vertex algebra and then take the constant part. So this is the way that I think Richard Borchers gave a seminar in Berkeley where he did that kind of construction. And that is in general, in constructing E8 from a lattice, you essentially do the zero mode computations of the vertex operator algebra. So, but there aren't, so those are our groups. In that case, the good representation, so there's always a good representation. So in the case of SUN, it's the vector representation, and similarly for SON, where the commutant, the invariant theory with these pictures is completely known. And in 1996, or probably before, Deline and Deman, Deline first, discovered that there's a kind of uniform representation, uniform description of these invariants, fixed point algebras, for the exceptional groups. It was a kind of experimental mathematics, but they discovered all sorts of remarkable things. So these behave very, very nicely. When you tensor the adjoint representation, so that's G with the group acting by conjugation with itself, you get 5 different representations, and there's a kind of uniform decomposition. So in we call that principal graph thing, or it's easier to say it in terms of principal graph for a point than I think planar algebra. And so that's kind of uniform for these exceptional things. Now, they did that using the program Lie, which computes tensor products of all sorts of things. So you just feed it in, and it will give you these answers out. And I must admit, I have used that. So I might be a groupie of somebody because I've done some computations. Well, this is also studied by Hans Fensel, and those of you that have been to Banff will have heard him talking about this exceptional, the invariant theory for the exceptional groups, and his trying to then do it for the quantum groups at roots of unity. Well, so in general, in this picture, you have a subfactor, which is given by taking this infinite tensor product and then just shifting everything by 1. And that is kind of, it has some extra data because it comes with this shift. And that sort of, even in Sorin-Popper's classification, that's kind of built in. And it means that where in the Vaughan picture, you would have 4 categories of bimodules, NM, MN, NN, and whatever the other one is, whatever I haven't just said. You only have 1 category of bimodules in this case, so life becomes a little easier, although I think whoever said it, if you do planar diagrams, you have to be a little more careful about the coloring. But anyway, there we go. Right. Well, now, in all of these computations, we get into a little bit of trouble if we don't have multiplicity 1 when we tensor representations, because it's very hard to say, to pick out a component if it's got multiplicity 2, 3, or 4. And I mentioned that already the vector representation has multiplicity 1 for everything, and that's why its invariant theory is rather easy. So now, that is going to be related to something which will be important for us, a Brouillard-type decomposition, a multiplicity-free tensor product. So if you take UN modulo one of these subgroups, so just blocks down the diagonal, which contains the maximal torus, then you know that the homogeneous space by Frobenius reciprocity, it's sort of got multiplicity 1. So every representation has multiplicity 1. And you can say exactly which representations occur. If you look at the Young diagrams, it's ones for which the first n1 things are equal, the first next n2 things are equal, and so on. So it kind of picks it out. And for these groups, you have this kind of P, where P must stand for something parabolic. And that's just increasing the group to an upper triangular group. That will give you your parabolic group. And And then you can ask the question, when do tensor products of irreducible representations of this shape and then another shape, n prime, have multiplicity? If you tensor them, do you only get each irreducible representation with multiplicity 1? Well, that happens, and then you go into algebraic geometry. Yes. No more of that here for the moment. It happens when G has an open dense orbit in G mod P cross G mod P prime cross G mod B, where B is just the triangular, the upper triangular matrices. So that's a quite simple thing. That just is paraphrasing, looking for the condition on lowering operators, that a vector in the thing has to be killed by lowering operators. That's the rule. And this was proved by Stembridge. So, I mean, he actually, so when this happens is a remarkable thing, because you have an open dense orbit, that's what, and then only finitely many orbits otherwise. So it's a kind of slightly funny thing, but known in representation theory under a different name before that, which doesn't use any algebraic geometry, and that's Matsuki decomposition, which can be proved just using analysis. And it generalizes the Brouillard decomposition, which is that if you take GLNC, I said you could write everything as a lower triangular times an upper triangular, and then that's a double, it is equivalent to this double coset decomposition, that if you take the upper triangular matrices and decompose the group as a double coset thing, then the symmetric group gives you a set of double coset representatives. And the open cell corresponds to this thing which of maximal length in the symmetric group. And so just this thing which flips things like that. Well, that's a sort of a group-like decomposition. Then we also have a Lie algebra decomposition, which is very simple, where we just say that, you know, we do this thing and we can decompose every matrix as a sum of a diagonal matrix, an upper triangular matrix, and a lower triangular matrix, just in an obvious way, just cut them like that. And that's a sort of the additive version of this Gauss decomposition. Well, for loop groups, there's an analog of this, so that's smooth functions from S1 into G. There's an analog, which is the Birkhoff decomposition, described in Graham Siegel's book. And that decomposition, if you apply it to a piecewise continuous loop, which actually you're not allowed to do, but Riemann said you could, and then Plemelge, or however you pronounce that, there might be somebody from that country here, or near it. Anyway, he said, so you take loops on intervals, say 3 intervals, which they take constant values in GLN, and then you want to apply the Birkhoff factorization to that. You can do it by introducing a function with some kinds of singularities and then apply this Birkhoff factorization, and then that implies the Riemann-Hilbert correspondence. That's probably not so well known, but it is quite useful for just saying that it's part of operator theory. Anyway. Well, now just something that I think everybody knows. Well, I hope probably everybody knows all of this. And if I might have said something which contradicts your knowledge. Right, so here is something, this is the mantra of this correspondence between modular forms and break groups. So the break group and the modular group. The break group on 3 strings, its center is full twist. And then you have the pure break group, which if you look at a braid and then just forget about under and over crossings, then you'll get an element of the symmetric group on 3 objects. Well, this says it doesn't permute the objects. So that's P3. Well, then you have, in number theory or whatever, you have this modular group, SL2Z, modulo its center. It's called gamma 1 usually, or perhaps 1 might be written in various different places. and I put a bar over it just to say that I'm only thinking of it as acting by Möbius transformations. And then I take inside that the congruence subgroup, so all the things that when you reduce modulo 2, you just get the identity. And then the basic thing is that the Bragg group modulo its center containing the pure Bragg group modulo its center, so that because we said it didn't permute the strings, the quotient must be the symmetric group on 3 objects. And then here we have SL2Z containing this. This has also got S3 quotient. These are the same. And if you want to write it out, you know, every time you have something in the center, you make it equal to 1. You have ABA equals BAB. That's the Bragg group relation. And then you can write that as AB cubed equals 1 and ABA squared equals 1. And then you use the fact that SL2Z is just the free product of Z mod 2 and Z mod 3. And that's it. So that's a kind of fairly useful way of passing from one to the other. Okay. Right, so fusion for loop groups. My loop group will be the loops on SU2 for the moment. So I'm just going to recall how, assuming that Vaughan-Jones exists and has done all his work, we could do fusion for SU2 with as little work as possible. That's the idea. So we somehow kind of we'll use the general theory of subfactors to kind of feed into that thing. So we don't really want to do too much. We don't want to get our hands too dirty. So the idea is to compute a very small amount of fusion explicitly and deduce the rest by Perron-Frobenius. That's a kind of, I think that there's probably some word in planar algebras which does something like that, where you have to do you have a little box and it does everything for you. It grows. It's a fish. I don't know. Anyway, but it's a. I mean, in these things, and it's very similar for any subfactor. That's what you want to do. So here, I'll tell you how you get the representations in a minute. For loop groups of SU2 at level L is an integer greater or equal to 1, you have this finite set of positive energy irreducible representations and the tensor product rules. So it's a kind of truncation of the list of irreducible representations of SU2. So you're only allowed spins up to L over 2. And then you have these truncated fusion rules. These first two, are the same as the classical ones. And only here, where you don't have something new to go to, do you just truncate. And that's that. And then you could play all sorts of games. You can compute quantum dimensions to make this multiplicative and additive. And then you'll find the quantum dimension of this, I hope I haven't got it wrong, is 2 cos pi L plus O plus 2. And then here, for the Jones-Wassermann subfactor, which is the mismatch between the commutants of loops on 2 sides, which gives a subfactor, that will have that quantum dimension squared. That will be the thing. And as you let L go to infinity, this will go towards 4. And so you've got these quantum things constructed from an infinite dimensional loop group which tend towards the classical just SU2 acting on the 2-dimensional representation in this infinite dimensional tensor product. So that idea about computing the fusion then is, well, you just compute first 2 things. So fuse H, this generating representation with itself, and then again. Right, well, you'll find that you have the trivial representation in there. So you take the projection onto the trivial representation, which in this case is the Jones projection. Or you could call it temporally Lieb algebra if you wanted, but it's a Jones projection. So E1, and then the projection in the second 2, E2, and you know that because that E1, E2, E1 equals 1 over d squared E1. So you've computed the fusion rules and the quantum dimension of the representation without having done everything. You've just done, this is what I mean by a little piece of the picture. Well, now, you know that the fusion rules that are sort of predicted over there, they're not equalities, but by the method of proof, which I'm going to show you, that one is definitely contained in the other, the right-hand side, in the other, the right-hand side is an upper bound for the left-hand side. On the other hand, by Perron-Frobenius, the quantum dimensions fill everything out, and so you've got everything. So that's the idea behind doing a tiny little bit of a computation, and then the rest is a kind of bootstrap method that gives you everything else. And that, for example, is the way Valerio Toledano Laredo did use it. This is a sort of, he got this from Hans Fenzel's work, how he did fusion for the vector representation of SON, loops on SON. So let just remind you how we construct positive energy representations of these groups. Now, when we first started doing this, Vaughan and I in Paris, I was interrupted at the blackboard. I can't even remember whether you were in the room. It was at the Collège de France, and I think Alain he went up and he just put a little box on the board with CAR inside. This is all you need. And in fact it was. I mean, it took a little while to work out why that was so. And so the canonical anti-commutation relations, and that is all we need. So what happens here, you take a Hilbert space, H, projection on it, and then the CAR algebra is defined by these anti-commutation relations. And given the projection, it defines an irreducible representation on fermionic Fock space. Now, I'm in Cambridge, so the P, the cutting into positive and negative, is Dirac. It is Dirac. He did it. So we have to, right, just in case anybody else is claiming to have done it. It was Dirac. Anyway, and we have things that we call Dirac Cs, which are suppressed for this talk, and so it's generated by a vacuum vector, which is killed by these annihilation operators, because that's what annihilation operators do, and equally well these operators, and that uniquely determines the representation. And if you're doing C-star algebras, you're given an irreducible representation of this star algebra, C-star algebra. You can specify it by a pure state, which is just given by that formula there. And that, in fact, for us historically, the paper of Powers and Sturmer is one of the things we looked at, where these pure states are and factor states are discussed more generally. So next thing you want to do is get a representation. So given a unitary on the Hilbert space, which is the pre-quantized thing for the CAR algebra, it defines an automorphism of the CAR algebra, just it's canonical. And then you can ask, when is it implemented in this fermionic Fock space, i.e. when is there a big unitary on the Fock space, which when you conjugate by it gives you this automorphism. And then the answer was given by Irving Siegel and probably David Shale. I mean, whatever. I mean, they were all together. Not Andre Weil, but Siegel, perhaps Andre Weil, I don't know. Anyway, this happens if and only if the commutator, so the additive commutator of U and P, is a Hilbert-Schmidt operator. So that means its entries, matrix entries, are square summable. And now, again, this can also be found in the book by the other great Siegel, Graham Siegel. So here's the example, which is a kind of Toeplitz example. You take H to be the L2 functions on the circle with the canonical orthonormal basis given by exponentials P. We're in Cambridge. It's the Hardy space projection onto the sum of things where the negative coefficients vanish, so boundary values of holomorphic things. Then the in this case, the loops so loops into the torus, semi-direct product of the diffeomorphism group satisfies Siegel's criterion, and so it acts projectively. And inside the on holomorphic Fock space, and inside it you have the rotations inside the diffeomorphism group, which act canonically, and these act with positive energy, so that if you look for eigenvectors of the quantized operator r of theta for rotations, you only get positive eigenvectors. So in fact, this loop group acts irreducibly, and in courses on conformal field theory, there are sort of 3 or 4 different ways of thinking about this. Is called fermion-boson duality, and you think of this, it's an abelian group which is acting projectively, and if you think about the Stone-von Neumann theorem, which tells you about projective representations of abelian groups that appear in quantum mechanics and physics, then you would get a representation on bosonic Fock space. So whereas fermionic Fock space was an exterior algebra, bosonic Fock space is a symmetric algebra. And so that's where that comes from. So that's that first observation. Well, we can do the same for this Hilbert space tensored with C2, and then we get loops on SU2 acting in that, and we can take direct sums, and when we do that, we get positive energy representations of loops of SU2 at level L. And they're classified by their lowest energy subspaces, i.e. you have the rotation group acting, you look at rotation invariant vectors, that's an irreducible representation of SU2, and so it's one of the list of representations, and the ones we get at level L are just these representations VI, where I is less or equal to L over 2. So that's kind of fairly simple. So the ghost of Con. Now, so the next thing we have to do is to compute confusion. And when I was there at the IGS, he gave me his private notes on bimodules computing various things, and that caused a lot of difficulty with me until I could find a slightly alternative way of doing his method of fusion of bimodules, which was then perfect for conformal field theory, at least just this example. So the definition for bimodules over von Neumann algebra, which Alain did, reduces to a 4-point function formula that's actually down there for loop group fusion. So that gives something which can be written in terms of loop group things. Well, you need some fields, and these are called spin-half primary fields, and they go between these irreducible representations, increasing the spin by a half or minus a half. And what they are the fermions just cut down to these representations. So we don't actually have to do anything. All their duals, you could take A of F stars, that will be equally good. And so we have those quantum fields there. We just know some how they might commute or not commute with loop group elements, that we know. We don't know any other information at the moment. And then the formula for confusion says, well, we should form a tensor product by forming a 4-point function. And in this case, we take x concentrated in one half of the circle, so smeared with something in one half of the circle. This f would be concentrated in one interval, and g in the complementary interval. So if these were fermions, and we did that, then the operators A of f would anti-commute with A of g and with the adjoint. So that's a fairly simple kind of anti-commutation relations, very simple thing with pluses and minuses. And in order to do this computation, we have to find a more complicated braiding relation for these x's and y's. This is the last slide where we talk about von Neumann algebras. But this was inserted because Vaughan wanted me to and I agree with him, have von Neumann algebras in some fairly central way. But it certainly tells you what to do, and you might not know otherwise. Not necessarily something easy, but there you go. So what you have to do to compute the fusion, you have to do some braiding. Now that is a kind of well-known thing in conformal field theory. There's a duality between fusion and braiding. And I think everybody who's probably done this kind of knows how that works. And it's certainly part of the Mohr-Seiberg, all those axioms they wrote down way back in the last century. So what you find out is I've just done two sets of braidings together. So I've braided x with y star, and then it's moved past, and then I've braided it again with this y. So I've done two sets of braidings, and the end result has this particularly simple form like that, where you have some numbers which have to be greater than 0. And then you can actually compute the fusion. I can see a mistake there. Sorry about that. So that's a half. So I'm fusing the spin half representation with itself. And then I just use this relation to give myself a unitary map from the definition of fusion in terms of that 4-point function and the thing I'm going to get I want on the other side. And that is a unitary map between the two. Well, I have to compute. So that's kind of shown you what, roughly speaking, the von Neumann algebra machinery would give you. You have to make sure all these operators are well defined. They could be unbounded. Here they're obviously bounded, but they could be unbounded. You then have all the work of Glim, Jaffe, Streeter, Whiteman, Yost. I mean, all of that kind of stuff on how to do quantum field theory using sort of Whiteman functionals, etc. And you have to just go through that and then check those sort of things. But because this is 1 + 1 dimensional theory, there are various tricks for doing that. So here you want these kind of relations. Well, in physics, you take vacuum expectations of 4, here the underlying thing, of these 4 fields, which would look like that. So there are 4 variables, Z1, Z2, Z3, Z4. Too many. I mean, that's not what we want. Well, if you know how, when you permute these, how it behaves, then there's a theorem, Bargmann, Hall, Whiteman, that tells you how to translate the monodromy properties of that thing into a braiding relation like that. And that works perfectly well in conformal field theory, so that's the thing one uses. Now this has 4 variables, which you didn't really want, but underlying this is a copy of SL2C, and so SL2Z can move 3 of these to 0, 1, infinity, and then what you're left with this function is something which is just an ODE in one variable of precisely the type we're talking about. So it's a symmetric Fuchsian type, and the braiding is given by the monodromy of that. Now, you could say that, in fact, here I have a symmetric group on 4 objects acting. And so why did I do S3 and not S4? But in this case, there's always an obvious way if you've got an S3 of getting an S4, namely you take first generator, second generator, and then the first generator again. And in these examples, that's what happens. So an apparent S4 is just not there. I mean, it's a little disturbing when you first see it, but it is what happens. Right. So now we go back to the 19th century, or possibly before it, and in the book of Ints. So we do the 2x2 case. So we got this kind of symmetric Fuchsian system, and well, the 2x2 case is just hypergeometric function. We open Whittaker and Watson, or we look at our favorite book, and Whittaker and Watson is not my favorite book because it does all these horrible Barnes integrals because he was English, and nobody uses those. So you have to look in another book, Hiller, say, or whatever, or Ints. Ints is perfectly good. So what do we know about those? Well, solutions are given by Euler integrals. So that already puts us back, way back. We're Swiss now. And then you've got these power series solutions, and where you have this kind of Pochhammer symbol. And then you want to compute the monodromy. Now, the monodromy is often computed by these transport formulas of computing the value of the hypergeometric function at 1. You go from 0 to 1. You want to transport solutions at the point 0 to solutions at 1. That's not, in fact, how we're going to do it. So that's a very computational way of doing it, and can't be done in general. But if you just want the monodromy, fixing a point and seeing how this changes, that can be done by pure thought. And that's how Ints does it in his book, as a kind of rigidity theorem which pre-shadows the way we're going to do it. So what you do, these generators, as you carry the solutions around 0, 1, infinity, the product will be equal to 1, because you just look at the thing. It's a fundamental group thing on the sphere. And on the other hand, from the local behavior at the singularities, you know that G0 that they have known eigenvalues. That's just known. Well, then there's the fact that we're going to use is if you have 3 generic subspaces, one-dimensional subspace of a 2-dimensional vector space, then they have a canonical form generically. And that is, there's one basis vector V1 for one subspace, another V2, so they don't intersect, that's generic. And then the third one is the graph of an operator, so in this case just V1 plus V2. Put that in there, you've computed the monodromy of the hypergeometric functions without doing any work. That is in fact more or less a slightly simplified version of the proof in Ints, and is the way we're going to do it. So you don't do any work. You just rely on this fact about generic subspaces. So you can forget von Neumann algebras for the moment. I mean, they won't reappear. So, well, in 2 dimensions, there is a geometric interpretation of this symmetric Fuchsian system. So there, you convert to an order 1 matrix ODE. You convert it by just looking at the entries into an order 2 scalar, a second order ODE. I mean, and in that case, you can convert it to something like this if you do an Euler integrating factor. So now this geometric interpretation, if you take P to be this kind of partial fraction, and then we remember this thing here, the Schwarzian derivative, which is this expression here, which has the property that if we do a fractional linear transformation on F and plug it in, so AF plus B over CF plus D, it doesn't change the Schwarzian. And in fact, that's sort of why it was invented, and Schwarz sort of invented it because he was doing these uniformization problems. And if we solve this with SF equals P, this solves the uniformization problem for a hyperbolic equilateral triangle if we've started from a symmetric system. So that will be in the upper half plane a triangle with all its angles equal. And then how do we actually solve this thing? So we take 2 linearly independent solutions of this Sturm-Liouville thing, which can be expanded as power series, and we take the quotient. And that defines a map from the upper half plane onto the interior of the hyperbolic triangle. Okay, so that's sort of, I mean, that's what Schwarz did. But he and Poincaré went a little bit further. If you take alpha to be pi over n, then you can tessellate. I should have had a picture, but alas, because I'm sort of computer illiterate, for the purpose of this, I haven't got it. You can look on Wikipedia, look under Schwarz triangle groups, those of you that have your iPhones handy. Then you can tessellate, and it's on the cover of all these books, you can tessellate the plane by these triangles in a beautiful way. And then, if you reflect in the sides and invert the function u over v, you get an automorphic form for that reflection group, the reflection group in the sides of that triangle. And you can get, I mean, it will have some anti-holomorphic things in. If you take something of index 2, you'll just get a usual usual Fuchsian group. Right. Well, then we're going to get this elliptic lambda function. This is one way of doing it. So if we let n go to infinity, so the angles go to 0, then we end up with a triangle which is an ideal triangle. So on the unit disk, the isosceles triangle with all the angles 0, but with the vertices on the unit circle. And then that well-known tessellation. I think this is wrong from the point of view of Wikipedia, which probably has 2 L's. Although there's a spell. When I wrote an article on tessellations, I got the right spelling. This is the wrong one. But it might be that it's the English spelling, or my spelling. Anyway, so what you get there is this fairy tessellation, which is known, it's on the cover of lots of books, and it's very interesting to do with continued fractions. And this gives a uniformization of the complex numbers with 0 and 1 removed. And the covering group is then realized with that isomorphism I did before by this modular group, a congruent subgroup for the prime 2, and it's a free group generated by those 2 fractional linear transformations. And the inverse map is customarily given in terms of theta functions, and so those theta functions are just given by this q series, so q to the n squared, where n goes either through half integers or integers. And there's some fourth powers there. Right. And then here, so that's for the Haupt module, whatever, for uniformizing for this gamma 2, and then you have this famous, I'm not going to put that number down because I would just be pretending to be Terry Gannon and I couldn't possibly pretend that. It's probably 1728 somewhere, or something somewhere. Anyway, it's proportional to that, so this is the famous J invariant, and then you find that the quotient S3 of the modular group modulo this congruent subgroup for the prime 2, it induces the anharmonic group of fractional linear transformations of lambda. So that S6 is seen there geometrically, kind of in this picture. Right, well, we are approaching, the end is nigh. So now, so we can do some gauge transformations of these things, and what we can do is you can do a Gannon-Bantai thing, which will, all the S3 symmetry will be removed. We can go to a six-fold quotient by doing sort of inverses of z goes to z cubed and z goes to z squared, moved around by some Möbius transformation, so it doesn't quite look like that, but it really is that. And then we can convert the differential equation to one of this type. So we have an A1 which has eigenvalues half and 0 with those multiplicities m plus 1 and m. A B1 which has, now these are like, if we exponentiate these, we get s squared equals 1 and t cubed equals 1. So we're kind of getting SL2z coming out, as he did. And B1 with eigenvalues a third minus a third 0 with those multiplicities. And then the C1, which is the thing at infinity, will just be the same as this thing for the symmetric Fuchsian system, so the same as that eigenvalue list. So we can convert it to, I didn't write your name down. Well, there's Gannon-Bantai form. I haven't written, oh yes, I have. Sorry. I just hadn't written it in a good color. Okay, right. So that's one thing we can do. And then, that's all the sort of things that Terry has done and lots of other people on sort of convert. And then we can convert it to a vector valued modular form. We just can gauge transform everything so that the pullback to the upper half plane of this form omega is invariant not just under the modular group, congruent subgroup modulo 2, but the full modular group. That's just a simple gauge transformation. That way we get rid of the symmetric group on 3 objects. And the way we do that is by saying the symmetric group on 3 objects, it has a copy of the regular representation just by those fractional and linear transformations in lambda. And that's how that works. So this is a kind of gauge transformation. Now here is the point. So now we want to compute this representation of the Bray group on 3 strings, or SL2Z. And what we know is that the operators we got the following problem, that we have a full flag, we have an element of order 3 which has 3 subspaces according to the eigenvalues. That defines a partial flag. And then we got an element with s squared equals 1. That just defines a subspace. But that result on the sort of rigidity of those things, that open cell, says that there's a unique, that can be put in a unique form generically, just as we had for 2 subspaces, V1, V2, and V1 plus V2 for the third. So this is the analog of that. And then that simply says that the operators T and R, so T is the cubed equals 1, R is this Bray group generator, they must satisfy this eigenvalue equation where EI runs through a basis, and then this dual thing. Now that practically pins them down uniquely. There's just one equation that you have to solve, and that is, so in these things, if you look at them, the one is upper triangular, the other is lower triangular, so lambda 1 and lambda 2 are lower triangular, and then you have to solve this equation, which is a non-commutative equation. But if you look at it, you just sort of say, oh, it is just the Gauss decomposition. So you do the diagonal things first, and that pins down y, and then you do the off-diagonal things using that Gauss, just that picture I drew, and that solves this completely. And that then is the version of this rigidity theorem that generalizes Wenzel and Tuba. So in the 3 minutes left, so that just does that. Now, there is more to this, because underlying this is this undergraduate thing, which is Katz's rigidity theorem, which is completely elementary, as done by Boykers, so Fritz Boykers. And that there's a theorem of Scott, which says if you got a representation of 3 objects, G0, G1, which generate a group and their product is 1, so we had that in this case, then there's and they act on a vector space, you have this inequality. It's a one-line proof. It's something that it's either linear algebra 1 or linear algebra 2. I think Dale Husemuller would have taught it in pre-calculus. Anyway, then that, without just applying it with W equals NV and 2 different actions, you then prove this rigidity theorem of Katz, which says that if you have 3 elements generating a group, as we've had here, and you look at the dimension of the commutant of each element, so you assume they're diagonalizable, and the sum of those satisfies this inequality, well, that's always true, And if equality holds, then you have this rigidity, which says every time you have elements with the same eigenvalue list, so pointwise, and the product is 1, then they're all jointly conjugate. So this is we've used it implicitly. Every time we can construct a representation of SL2Z with these eigenvalue lists, any two would be the same because this criteria is satisfied. So again, although it was very hard to prove this, Völklein and Stambach, and then simplified again by Beukers, have a completely elementary proof of this, which you could teach your undergraduates, although they might never come to another class by you again. And then there's a similar result for sums of elements. This is products. You have a similar thing for that. And now, just very quickly, if I'm allowed. So there is a process within this thing of Katz who did, it was algebraic geometry and various things on moduli space, which has been Detweiler and Reuter have got a very simple process which is written down here for passing from an n-dimensional system to an n-1 dimensional system or n+1 dimensional system. So that works for the monodromy, and it works for the differential equation that you're trying to solve. And they are compatible. So if one thing is the monodromy of the other, when you do this process of middle convolution, the result is also the monodromy of that new system. And in addition, it's kind of effective in that there's this Euler transform which allows you to actually write down the solutions. So in the case here of these things, you could actually, with a computer, and certainly there's some Japanese people who've done this in a slightly different setting, have kind of done that process of being able to write down closed forms for the actual differential equation as multiple integrals. So kind of just, it's a machine. Right. So, and then at the end, so since we're in Cambridge, well, this same circle of ideas, which if you add modular equations, which are part of moonshine, so we're all CFT people in this room, so moonshine is thrown in, was already used for proving the formulas for 1/pi by Ramanujan in his private notebooks. So this relation between modular forms and ODEs, the various transformations going from one form to the Terry-Gannon and Bante form, etc. And so he was able, with that, to sort of have a hypergeometric type series for 1/pi. And this series is actually in a Walt Disney film called High School Musical, where this brilliant girl notes that when her teacher writes it on the board, she's got a factor of 2 wrong on one side and corrects it to the right one. And then the teacher says, no, that's wrong. And then the teacher sits down and says, no, you were right. So she's a genius. She's called Gabriela Montez. Not that that's the character, not the real actress or actor who played it. And so this is part of that elliptic functions to alternative bases, so it's completely stupid. And in this world of Mr. Trump, that kind of theory which people have only recently been able to understand. So there's another thing of that nature, again with this all these modular equations which Terry introduced to explain various bits of moonshine, and it's part of moonshine. So this is another one of these, and the people that work on this are brothers or possibly even twins, the Borwin brothers or the Chudnovsky brothers. So the Chudnovsky brothers in 1989 used this thing. Now we're in the world of, I think they're in the States where everything is very big. And so they were able to prove, using this thing which converges very rapidly, they were able to compute pi to over 2.25 billion decimal places. So they were making America big. That's it.
We'll take one question now and probably postpone the rest for tea. One question for Anthony. Doesn't mean to be that discouraging. Well, let's take Anthony again now. 10 past 10.